Let's solve problem 8.55 for Microelectronic Circuits 8th edition by Sedra and Smith. We're given this common gate amplifier circuit, and there are 6 parts total to this problem. Right now I just have the first 2 shown on the screen. We're told that Q2 and Q3 are matched, and Kn prime W over L is also equal to Kp prime W over L, and that is 8 milliamp per volt squared. We also know that all transistors have the same Thevenin voltage and early voltage. Lastly, we're told that the signal Vsig is a small sinusoidal signal with no DC component. Before I start solving part A, let's discuss what's actually happening in the circuit. So we see that Q3 and Q2 are both PMOS devices because the arrow is pointing at the top. Q1 is an NMOS transistor cascaded with Q2. But take a look at this wire here, going from the gate of Q3 and Q2 to the current source. So what we're doing with this wire is we are shorting the drain of Q3 to its gate, as well as the gate of Q2. And this creates what's called a current mirror. So Q3 and Q2 create a current mirror, where because we are shorting the gate of Q2 to the drain of Q3, which has the current source, we know that the drain current at Q2 is equal to the drain current at Q3. And because Q2 is simply cascaded with Q1, we can already solve the first part of part A, asking for the DC drain current of Q1, because we can tell, based off this information, that the same current is traveling through the entire circuit. So that's the answer to part A, the first part of it. The second part asks for the required value of V bias. Now this part's a little bit more tricky. How can we solve for V bias? Well, it would be helpful if we could put V bias in terms that we are more familiar with. So to do this, I want to start at the bottom of the circuit, down here. And our goal is to travel up to V bias using terms that we already know. So if we start down here at ground, right, and we're neglecting the effective early voltage, and we're also just considering the DC value of V bias. Because Vsig is a small sinusoidal signal with no DC component, we can ignore Vsig when trying to calculate what V bias is equal to. So we're going to just skip past Vsig because it has no DC component. Now we passed this resistor here, so we're going to need to add the voltage drop across that resistor, which is ID1 times R, or 100 ohms. And lastly, we just need to get to the gate of Q1 because that is where V bias is. So we just need to add the voltage drop from gate to source at Q1. And this is how we would be able to find V bias. So now we just need to try to solve for the voltage from gate to source because we already know the current and we already know that the resistor is just R, or 100 ohms. Well, I know that the voltage from gate to source of a transistor is equal to Thevenin voltage plus the overdrive voltage, and we're already given Vt. We can see it's equal to 0.5 volts. So all that's left is to solve for the overdrive voltage. And to find the overdrive voltage, we can leverage the drain current equation. So know that ID is equal to 1/2 Kn prime times W over L times V overdrive squared. V overdrive is the only term that we do not have the value of, so we can simply isolate it. So we will say that V overdrive is equal to the square root of 2 times the drain current divided by Kn prime times W over L. And that's going to be, if we plug in the terms, 2 times 100 microamps divided by 8 milliamp per volt squared. Be cautious that the drain current has the unit micro, which is 10 to the negative 6. and K in prime W over L is in milliamp, which is 10 to the negative 3. And then if I crunch these numbers, we should get that V overdrive is equal to about 0.158 volts. So I know that now I can calculate my voltage from gate to source. It's going to be the Thevenin voltage, 0.5 volts, plus 0.158 volts. So that's going to be 0.658 volts for the voltage from gate to source. And now I can calculate my V bias by just simply adding that extra current times resistance. So we have V bias is equal to the drain current, which is 100 microamps, times the resistance, which is 100 ohms, plus that voltage from gate to source, which you already calculated, so that's 0.658 volts. And that should get us 0.668 volts. Really squeezing everything in here. So for part A, the DC drain current is 100 microamps, and the required value of V bias we solved for 0.668 volts. Let's continue with part B. Okay, so part B asks for us to find the values of the transconductance and the output resistance for all the transistors. And thankfully, because we know that Q3 and Q2 are matched, we know that all transistors have the same K times W over L, they all have the same Thevenin voltage and early voltage, that the transconductance and output resistance should be the same for all of them. And we can also just mathematically prove this by just solving for it. So the output resistance will be VA over the drain current. So all the transistors have the same early voltage, it's 5 volts. All transistors have the same drain current, which is 100 microamps. So that would be 50 kilo ohms for the output resistance. And then for the transconductance, we can just leverage the equation 2 times the drain current divided by V over drive, which we calculated in part A, and that is also the same for all the transistors. So it's 2 times 100 microamps divided by V over drive, which we calculated to be 0.8 volts, 0.158 volts. And then if we run these numbers, I get 1.266 millisiemens. So that is our answer for part B. Let's move on to part C. Alright, let's continue with part C. We want to find the value of Rin, which is denoted here in the figure. So how do we solve for Rin? Well, Sedra and Smith provides an equation for us based on the common gain amplifier. Really, any amplifier in general, as long as you have Rin denoted, it will be the output resistance of the transistor we're looking at. So in this case, Q1. Maybe I denote that here in the equation. So we want the output resistance of Q1 plus any load resistance, which I will explain shortly, divided by 1 plus GMRO, again, of the transistor we're looking at, which based on this arrow, we see that the first transistor we see is Q1. But what is RL? Well, RL is just any load resistance. And you can see it's also denoted here, RL. And you can see RL is looking at Q2, which makes sense because Q1 is in cascade with Q2, meaning Q1 is loaded with Q2. And what's the resistance of Q2? Well, it's just the output resistance of Q2, which we already calculated to be 50 kilo ohms. So from there, we should be able to solve for Rin as 50 kilo ohms plus 50 kilo ohms divided by 1 plus the transconductance, which we solved for, 1.226 millisiemens, multiplied by 50 kilo ohms again. And we crunch some numbers. I get that Rin is equal to 1.226 0.555 kilo ohms. So this is the input resistance seen by the transistor Q1. And for part D, to solve for R out, again, you really just need to follow the arrow that they already marked for you in the figure. So if we're following R out, that means we're starting here at the output, and we're going to just travel down. So we see that we first hit Q1, so I'm going to write RO Q1, and we're just walking down the circuit in series. So the next thing I need to add is this 100 ohms, or as a general expression, the signal resistance, RS. And lastly, because of this voltage source here, Vsig, we also need to account for the transconductance times the output resistance of Q1 times that signal resistance, or just the 100 ohms. So if I numerically solve for this, it would be 50 kilo ohms plus 100 ohms, and then essentially just concatenating those two resistances together with the transconductance in mind for the signal, we would do 1.226 millisiemens times 50 kilo ohms times 100 ohms. And then if I run some calculations, I get 56.43 kilo ohms. So this is the resistance seen by the output. So if I'm standing at here, R in, I would see 1.5 kilo ohms. And if I'm standing here at the output voltage and I look down, I would see 56.43 kilo ohms total. Let's move on to part E. Alright, so for part E, we want to solve for the voltage gains VO over VI and VO over Vsig. And because we don't know the actual voltage values, another way that we could solve this is by representing each of these voltages by their equivalent resistances. So for example, the equivalent resistance for Vin would just be Rin. We see Vin here, and Rin is labeled directly equivalent to it. So what would the equivalent resistance be for Vsig? Well, if we're just looking at Vsig and we try to follow, it's just Rin in series with this extra 100 ohms. So it would be Rin plus 100 ohms. But what about Vout? You may be tempted to use Rout, but this would be incorrect. Rout represents the resistance following the output voltage. We want to use the resistance that precedes the output voltage, and that would be RL. So if I wanted to solve for Vout over Vin, I would just use the equivalent resistances, RL over Rin. So that would be 50 kilo ohms divided by 1.555 kilo ohms, as we solved in the previous part. And that would be 32.18 volt per volt would be our unit. Actually, I get 0.15, sorry. And I know it doesn't ask for it, but just for clarity, we could also solve for example, VI over Vsig. And that would be Rin divided by Rin plus 100 ohms, where Rin is just 1.555 kilo ohms. So you can see that Vin over Vsig would actually be less than 1. It would be, if I calculate it, 0.939 volt per volt. And if we wanted to do Vout over Vsig, we could just use those equivalent resistances again. I will also just show a quick little trick. If you're ever in an exam and you're in a pinch, you can just do Vout over Vn multiplied by Vn over Vsig if you don't have that calculation directly. So that would just be 32.15 volt per volt multiplied by 0.939 volt per volt, and that's equal to 30.19 volt per volt. Again, you could also just do V out over V sig is equal to RL over Rn plus 100 ohms, and you would obtain a very similar result. Let's move to part F. Alright, we have reached the last part of the problem, which is arguably the hardest. It is to solve for V sig and how large it can be from peak to peak while maintaining saturation mode. I usually use this caret symbol to represent peak to peak voltage. Now this is very hard to calculate directly, but what we could do is calculate the peak to peak output voltage, and then we can leverage that V sig from peak to peak would just be the peak to peak output voltage divided by that gain, which we calculated earlier. So how do we solve for the peak to peak output voltage? Well, it would just be simply finding the maximum output voltage, finding the minimum output voltage, and then just subtracting those two values. So how can we find the maximum output voltage to start? Well, we would do that by traveling from the top of the circuit until we reach the output voltage here. So if we start at the top of the circuit, that would be 1.8 volts. And then to get to the output voltage, we would get here, and we need to subtract the voltage from source to drain at Q2. But we know that in order to maintain saturation mode, the minimum this could be would just be V overdrive. So it would be 1.8 volts minus 0.158 volts, calculated this earlier. So the maximum output voltage we can have is 1.642 volts. Now, what's the minimum voltage? Well, I already know the voltage here at V bias, so I really just have to get from gate to drain. And we know that that would just be the bias voltage minus the Thevenin voltage. So the minimum output voltage would be V bias, sorry for my handwriting, minus Thevenin voltage. So that would be equal to 0.668 volts minus 0.5 volts for Thevenin voltage, and that would be 0.168 volts. So that means the peak-to-peak output voltage is equal to 1.642 volts minus 0.168 volts, and that is equal to 1.474 volts. So now all I have to do to calculate V sig is take my peak-to-peak output voltage, which is 1.474 volts, and divide it by the gain, which we calculated in the previous problem to be 30.19 volt per volt. And that would be equal to 0.046 volts. So that is the largest value that V sig can be, or peak to peak. And that completes the problem. Thank you for watching the video. For any questions, feel free to leave a comment or email me, and have a great day.